Welcome. In this video, we will explore the properties of curves using calculus. This topic is fundamental to the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to find the equations of tangents and normals to a curve, and you will be able to solve more complex problems involving these concepts. Let's begin with an opening problem to set the stage. Consider the curve I equals x cubed minus 4x. What features can you describe? How can calculus help us identify them? Looking at the graph, we can see it has two turning points, a local maximum at B and a local minimum at D. It also passes through the origin, C. Calculus provides the tools to find these points precisely and to describe the curve's shape. In this chapter, we will use derivatives to find tangents and normals, turning points, and inflection points. We'll start with tangents. First, let's define a tangent. The tangent to a curve at a point A is the best straight-line approximation to the curve at that point. For many curves, like a circle or a parabola, the tangent line simply touches the curve at a single point. However, it's important to note that for some functions, the tangent may intersect the curve again somewhere else, or even pass through the curve at the point of tangency itself. This latter case is called a point of inflection. The key idea is that the gradient of the tangent line at a point is given by the derivative of the function at that point. So, if we have a curve y equals f of x, and we want the tangent at a point with x coordinate a, the gradient of that tangent is f prime of a. Using the point gradient form of a straight line, the equation of the tangent is y minus f of a equals f prime of a times the quantity x minus a. This can also be written as y equals f prime of a times x minus a plus f of a. This formula is crucial for finding tangent equations. Let's work through an example. We need to find the equation of the tangent to the function f of x equals the square root of x squared plus 5 at the point 2, 3. First, we need to find the derivative f prime of x. It's easier to differentiate if we write the function with a fractional exponent. So f of x equals the quantity x squared plus 5, all to the power of 1/2. We'll use the chain rule here. The derivative of the outer function, u to the 1/2, is 1/2 u to the negative 1/2. The derivative of the inner function, x squared plus 5, is 2x. Applying the chain rule, a prime of x is 1/2 times x squared plus 5 to the negative 1/2 times 2x. Simplifying this, the 1/2 and the 2x cancel, leaving us with x over the square root of x squared plus 5. Now we need the gradient at our specific point, where x equals 2. We substitute 2 into our derivative. F prime of 2 is 2 over the square root of 2 squared plus 5, which simplifies to 2 over the square root of 9, or 2 over 3. This is our gradient. We have the gradient, m equals 2 to 3, and the point of contact, 2, 3. We can now use the point gradient formula. I minus 3 equals 2, 3 times the quantity x minus 2. Distributing the 2, 3 gives y minus 3 equals 2, 3x minus 4, 3. Adding 3 to both sides, which is 9, 3, gives our final equation, y equals 2, 3a plus 5, 3. Let's look at a different type of problem. Finding horizontal tangents. We need to find the equations of any horizontal tangents to the curve uy equals x cubed minus 12x plus 2. The key property of a horizontal line is that its gradient is 0. Therefore, to find horizontal tangents, we need to find the points where the derivative of the function is 0. First, we find the derivative, dy by dx. The derivative of x cubed minus 12x plus 2 is 3x squared minus 12. Next, we set the derivative equal to 0 and solve for x. We have 3x squared minus 12 equals 0. Factoring out a 3 gives 3 times the quantity x squared minus 4 equals 0. This is a difference of squares, so we can factor it further into 3 times x plus 2 times x minus 2 equals 0. This gives us two possible x values where the tangent is horizontal. X equals negative 2 and x equals 2. These x values correspond to the turning points of the curve. To find the equations of the tangents, we need the y-coordinates of these points. When x is 2, y is 2 cubed minus 12 times 2 plus 2, which is 8 minus 24 plus 2, or negative 14. So one point of contact is 2. negative 14. When x is negative 2, y is negative 2 cubed minus 12 times negative 2 plus 2, which is negative 8 plus 24 plus 2, or 18. The other point of contact is negative 2, 18. Since the tangents are horizontal, their equations are simply y equals the y-coordinate of the point of contact. Therefore, the two horizontal tangents are y equals negative 14 and y equals 18. Now let's tackle a more advanced problem. We need to find the equation of another tangent to the curve y equals 1 minus 3x plus 12x squared minus 8x cubed, which is parallel to the tangent at the point 1, 2. The key here is the word parallel. Parallel lines have the same gradient. So, our first step is to find the gradient of the tangent at the given point 1, 2. First, we find the derivative, dx. The derivative of 1 minus 3x plus 12x squared minus 8x cubed is 3 plus 24 minus 24 squared. Now, we evaluate the derivative at x equals 1. dx at x or 1 is Masha 3 plus 24 times 1 minus 24 times 1 squared, which equals 3. So, the gradient of the tangent at 1, 2 is 3. Since the new tangent is parallel, it must also have a gradient of 3. We need to find another point on the curve where the gradient is 3. We set our derivative equal to 3, so it's 3 plus 24 minus 24x squared equals 3. Adding 3 to both sides gives 24 minus 24x squared equals 0. Factoring out 24x, we get 24 times the quantity 1 minus x equals 0. This gives us two solutions, x equals 0 and x equals 1. The solution x equals 1 corresponds to our original point. The new point of tangency is at x equals 0. Now we find the y-coordinate for x equals 0. When x is 0, y is 1 minus 3 times 0 plus 12 times 0 squared minus 8 times 0 cubed, which is 1. So the new point of contact is 0, 1. We now have the gradient, m equals 3, and the new point of contact, 0, 1. We can write the equation of the tangent. Using the point gradient form, y minus 1 equals 3 times the quantity x minus 0. This simplifies to y equals 3x plus 1. This is the equation of the other tangent. Let's move on to the second main concept, normals. A normal to a curve is a line that is perpendicular to the tangent at the point of contact. Visually, if we have a tangent line touching the curve at a point, the normal line passes through that same point and forms a 90-degree angle with the tangent. The key property of perpendicular lines is that the product of their gradients is 1. This means their gradients are negative reciprocals of each other. So, if the gradient of the tangent at x equals a is f prime of a, then the gradient of the normal at that same point is negative 1 over f prime of a. Using the point gradient form again, the equation of the normal is y minus f of a equals negative 1 over f prime of a times the quantity x minus a. This can also be written as y equals negative 1 over f prime of a times x minus a plus f of a. This formula is essential for finding normal equations. Let's work through an example. We need to find the equation of the normal to the curve y equals 8 over the square root of x at the point where x equals 4. First, we need the point of contact. We are given x equals 4. We find the corresponding y value by substituting into the original equation. When x is 4, y is 8 over the square root of 4, which is 8 over 2, or 4. So the point of contact is 4, 4. Next, we need the gradient of the tangent at this point. We find the derivative, dy-dx. It's easier to differentiate if we write y as 8 times x to the power of negative 1/2. Using the power rule, x is 8 times negative 1/2 times x to the power of negative 3/2, which simplifies to negative 4 over x to the power of 3/2. Now we evaluate the derivative at x equals 4. Dx at x of 4 is negative 4 over 4 to the power of 3/2. 4 to the 3/2 is the square root of 4 cubed, which is 2 cubed, or 8. So the gradient of the tangent is negative 4 over 8, or negative 1/2. Now we can find the gradient of the normal. It's the negative reciprocal of the tangent's gradient. The gradient of the normal is negative 1 over negative 1/2, which is 2. So the normal has a gradient of 2. We have the gradient equals 2, and the point of contact, 4, 4. We can now write the equation of the normal. Using the point gradient form, y minus 4 equals 2 times the quantity x minus 4. Distributing the 2 gives y minus 4 equals 2x minus 8. Rearranging into the form x plus by equals c, we get 2x minus y equals 4. This is the equation of the normal. Let's consider another advanced problem. We need to find the equations of the tangents to the parabola y equals negative x squared plus x plus 2, which pass through the external point, 1, 3. This is different from our previous examples because the point, 1, 3, is not on the curve. We need to find the points of tangency first. Let's call a general point of tangency, AYA. The y-coordinate is found by substituting a into the curve's equation, so YA equals negative a squared plus a plus 2. Next, we find the gradient of the tangent at this general point A. The derivative, dx, is negative 2x plus 1. So the gradient of the tangent at x equals a is negative 2a plus 1. Now we can write the equation of the tangent at the point, AYA, using the point gradient formula. I minus the quantity negative a squared plus a plus 2 equals the quantity negative 2a plus 1 times the quantity x minus a. We know that this tangent line must pass through the external point, 1, 3. So we can substitute x equals 1 and y equals 3 into this equation. 3 minus the quantity negative a squared plus a plus 2 equals the quantity negative 2a plus 1 times the quantity 1 minus a. Now we have an equation with only one variable, a. Let's solve it. Expanding both sides gives a squared minus a plus 1 equals 2a squared minus 3a plus 1. Rearranging gives a squared minus 2a equals 0. Factoring gives a times the quantity a minus 2 equals 0. This means a equals 0 or a equals 2. There are two possible points of tangency. We now find the equations of the two tangents. For a equals 0, the point of contact is 0, 2, and the gradient is 1. The tangent equation is y equals x plus 2. For a equals 2, the point of contact is 2, 0, and the gradient is 3. The tangent equation is y equals 3x plus 6. Let's look at a problem involving a common tangent. We have a quadratic y equals x squared and a logarithmic function y equals ln x. They touch at a single point. The key principle here is that if two curves touch at a point, they share a common tangent at that point. This means two things must be true. First, the y values of the two curves must be equal at the point of contact. Second, the gradients of the two curves must be equal at the point of contact. Let's call the x-coordinate of the point of contact b. From the first condition, a times b squared must equal ln b. From the second condition, the derivative of x squared, which is 2ax, must equal the derivative of ln x, which is 1 over x. So 2ab equals 1 over b. We now have a system of two equations with two unknowns, a and b. Let's solve for them. From the second equation, 2ab equals 1 over b. We can solve for a. Multiplying by b gives 2ab squared equals 1, so a equals 1 over 2b squared. Now we substitute this expression for a into the first equation. We get 1 over 2b squared times b squared equals ln b. The b squared terms cancel, leaving us with 1 over 2 equals ln b. To solve for b, we exponentiate both sides with base e. B equals e to the power of 1/2, which is the square root of e. So the x-coordinate of the point of contact is the square root of e. Now we can find the value of a. A equals 1 over 2 times the square root of e squared, which is 1 over 2e. So a is 1 over 2e. Finally, we find the equation of the common tangent. We have the gradient and the point of contact. The gradient is 2ab, which is 2 times 1 over 2e times the square root of e, simplifying to 1 over the square root of e. The point of contact is square root of e 1/2. Using the point gradient formula, y minus 1/2 equals 1 over the square root of e times the quantity x minus the square root of e. This simplifies to y equals x over the square root of e minus 1/2. This is the equation of the common tangent. Let's recap what we've learned. We've seen how to find the equation of a tangent line using the derivative to find the gradient. We've also learned how to find the equation of a normal line. which is perpendicular to the tangent. We've worked through several examples, including finding horizontal tangents, tangents from an external point, and common tangents between two curves. These are all key skills for the IBAA-HL exam. Now, to help you solidify your understanding, here are 5 practice questions in the style of the IB exam. Pause the video, try them on your own, and then resume to see the fully worked solutions. Here are the questions. Question 1 involves a tangent to a rational function. Question 2 asks for a normal to a trigonometric function. Question 3 is a common tangent problem. Question 4 involves finding a tangent from an external point. And question 5 is a proof involving tangents to a parabola. Let's go through the solutions. For question 1, we find the derivative using the quotient rule, evaluate it at x equals 2 to get the gradient, and then use the point gradient formula to get the tangent equation y equals 2x plus 5. For question 2, we find the derivative of sin 2x using the chain rule, which is 2c dasad 2x. At x equals pi over 4, the gradient of the tangent is 0. The normal is perpendicular to a horizontal line, so it's a vertical line. The equation is x equals pi over 4. For question 3, we use the common tangent conditions. The y values are equal at x1, giving a plus b equals 2. The gradients are equal at x1, giving a plus 2 equals 6. Solving this system gives a equals 4 and b equals 2. For question 4, we follow the external point method. We find the derivative, 2x minus 4. We set up the tangent equation at a general point A and substitute SAT 0, 0. This gives a squared minus 4a plus 5 equals to 0. The discriminant is negative, meaning there are no real solutions for a. Therefore, no tangents pass through the origin. For question 5, we find the tangent equations at x equals s and x equals c. We then set the y values equal to find the x-coordinate of their intersection. After some algebra, we find that x equals the quantity s plus t, all over 2, which proves the conjecture. I hope this video has provided a clear and rigorous explanation of tangents and normals, and has equipped you with the skills to solve a variety of problems. Keep practicing, and you'll master this topic.